All right, now we want to take a look at the reaction of this scope to the triangle wave. Like I said before, we've now proven that the vertical linearity with voltage is there. We're able to measure DC volts by movement of the beam accurately through all of our ranges. And then we measured our frequency response to the time base, and our time base was accurately portraying the trace the way that it needed to through all of its ranges. And this is where we put it together. We're looking at a triangle wave. You know what a triangle is. It's a straight line at an angle with another straight line at an angle, and in this case you imagine that there's a line across the bottom that would complete the triangle, but this is a waveform, so it's continuous, and it's only understood that the base is there. But what you're looking for is, does it look like a triangle? Does it look like two straight lines? If it does, at the speed that it's working at, it's building this triangle in a truthful linear fashion, and it's not distorting it. So therefore, it's if you can believe the frequency is right and the voltage is right, then and the linearity is here, then it's functioning beautifully. So now as I progress through the frequency ranges, if I can maintain the linearity of this triangle waveform, then I know, because I was measuring voltages properly and frequency properly, that I am portraying this frequency accurately, because otherwise it would be a distorted waveform. The fact that I didn't distort it means I portrayed it accurately. So let's give it a go. Right now we are running about 10 hertz, and we see that we have linearity. If I kick her up to 100, we still have linearity. We're going to expand the waveform so it's easier to see. No problem there. Let's take her up. This would be 1,000 hertz, right about there. Kick my intensity up a little. I'm doing fine. Let's go to 10,000. No problem with linearity here. Alright, let's go. We are at about 100,000. No problem here. There's 1,000,000. No problem there. We're at the end of our range. The only thing that would happen now is that we would put more triangle waves across the screen. Okay, so we'll sweep our frequency up now. Here we are at 2 megahertz. Let's go to 5. That's 5 megahertz. And what we'll do here is we'll expand the screen by 5. Kick up our intensity a little bit. We're still linear. Alright, so we're at 15 and climbing still. Here's 16. 17. Now you can see that we're shrinking. 18, 19, 20, 21. We're at the limit of my my generator right now, but still holding our linearity on the screen. So although this is beyond our frequency response and we've definitely dipped below the 3 dB line, we're still linear in our display of the waveform. Okay, let's move on. Okay, at this point I've moved to channel B, and I am right now at the limit of my generator's capability. We're running about 21 megahertz in here, and as you can see, it looks very similar to channel A in that we still have the linear shape. I'll back off to 15 and we'll just take a look at what 15 looks like. There's 15 right there. So we're in good condition, and we'll move on. Well, here we are testing the XY capability of this scope, and to do it, I've recreated a little experiment that I've done several times before. This is a 455 kilohertz ceramic resonant filter, and I'm feeding it with a signal that varies between 400 and 600 kilohertz from this generator. Feeding it through it, and I'm using the ramp output of the generator to drive the X portion, the B circuit, give me the time base, and then I'm feeding the signal of the resonant circuit into the channel A. And what we can see is, as we start from left and go to right, we start low in frequency and we wind up very high in frequency on the right. And in between, we hit this resonant peak. It's quite large. And that's the 455 kilohertz resonance that's there. And I can speed up the sweep rate, and you'll see that that resonant peak starts to look like it's drawing back on the screen. That's partially the phosphor not being able to show the trace because it's not there long enough. And as I slow the trace down, you can see that the peak becomes quite exaggerated, but you don't see the envelope of the wave anymore. So it's an interesting little experiment. And then I can show you here that if I don't go through the resonant chip anymore and I go directly without it, and you get this kind of a waveform. You don't see the resonance anymore. Basically, you just see the sweep envelope. And well, the other thing we can do is to disconnect the sweep from there, and we can run a jumper from A to B. Now we're feeding the same signal on channel A and channel B, and we should be able to see a Lissajous figure. In this case it's an oval because the signals are same basic on both inputs. So we have a good working XY system here. You can play around with it, do some Lissajous figures. You can look at transfer functions of different elements. Have fun with it. I have, and I will. So, okay. So once again, we'll be getting this scope that functions excellently. Passed all of its tests for vertical linearity, voltage capabilities, time base is accurate, and we have complete linearity throughout the frequency range, and we have the frequency response to beyond 15 megahertz at the 3 dB point. So what more could you really ask for? I mean, there's a lot of scopes today can't do that. We have plenty of brightness in the oscilloscope tube, and it comes with a manual, operation and service manual, and 2 probes. You got the complete package right here, and at this price it's a deal. So good luck, everybody, and happy bidding. Bye.